Hi viewers, welcome to my class on mechanics of materials. In today's class, we will work out another numerical example on shear force and bending moment diagram for a cantilever beam subjected to various types of loads. Let us work out. A cantilever beam is loaded as shown in figure. Draw the shear force and bending moment diagram for the beam. The cantilever beam is fixed at end A and subjected to a couple of 100 kN meter and a point load 30 kN at B and subjected to a triangular load with a major intensity 20 kN per meter. Now as a first step, let us find out the reactions at the supports. Already the direction of reactions are shown. At A there is an upward reaction. Also there is a resisting moment in the anti-clockwise direction. Now let us find out these reactions at the supports. Now let us take the force summation first and find out the reaction at the support. So you can take the force summation in the y direction. That will give RA, reaction at A, RA. Let us take upward because all the forces are downward. RA minus 30 minus the resultant of this load. Resultant of this load is area of this triangle, that is half of base, that is half of 2 into height. Height is intensity 20, so half of 2 into 20, which will give 20. So plus RA minus 30 minus 20, that is equal to 0. That is the summation. So you get RA as 50 kN. So the reaction at A is 50 kN. So you got the reaction here. Then to find out the resisting moment or reaction moment at A, you can go for the moment summation with respect to A. So summing up the moments, minus M, I have taken it as anti-clockwise, so minus M plus 30 into 2 clockwise moment. This point load is producing clockwise moment, plus 30 into 2. This is an anti-clockwise couple, so minus 100, and the resultant of this load is half of 2 into 20, which is 20, which will act at a distance of 1/3 of span from C, from major intensity side. So 1/3 of 2, that is 0.667 meter, or from 0 intensity side it is 2/3 of span. 2/3 of span over which the load acts is 2/3 of 2, or 1.333 from D. So from C it is 0.667 and the resultant load is 20 kN. So the 20 kN, the resultant load will produce a moment of 20 into 3 plus 0.667 or 3.667. That is the moment of this resultant load. So let us sum up the moments. Minus M, this is anti-clockwise, so minus M minus 100, because this is anti-clockwise coupled, minus 100. 30 into 2 clockwise, the resultant load is 20 into 2 by 2, that is nothing but the area of the triangle, into 3.667, 3 plus 0.667 from the higher intensity side. So that will give the M as 33.34 kilonewton meter. So resisting moment at A is 33.34 kilonewton meter. So after getting the resisting moment and reaction at A, we can calculate the shear force and bending moment. Now let us calculate the shear force at various sections. Now the reaction we got RA, vertically upward 50 kN, and resisting moment or reaction moment 33.34 kN meter, anti-clockwise direction. Now here no load is acting between A and B, so you can only consider one section. So shear force in this section AB is constant. We can calculate the shear force for the section AB anywhere between A and B. So shear force for the section AB, when you take the left side forces, there is only one force 50 kilonewton. That is the reaction at A. This couple will not produce any change in shear force. So plus 50, it's upward, so plus 50. So shear force for the section AB is plus 50 kilonewton. Now when you move to the next section, one more force is added, so that is minus 30 downward force. So for this section, shear force for that section is 50 minus 30 or 20 kilonewton. Now when a UVL or UDL acts, you have to calculate shear force both the ends, that is right of C and left of D. Now let us take the section immediately right of C. Immediately right of C, if you take, this is not a point load, it's a distributed load. Intensity is shown, so immediately right of C, the part of load is added is negligibly small. It is infinitesimally small distance right of C, so the part of load is negligibly small. This intensity is 20 kilonewton for 1 meter. So for 1 meter length, it is 20 kilonewton. Is the intensity this part and nearer to C. So it will decrease. The intensity is decreasing continuously to 0. So when you are taking infinitesimally small distance away from C, the part of load is 0 or negligibly small. So immediately right of C, there is no load acting here. So only this summation, which we have already got earlier, 20 kilonewton, will be the shear force immediately right of C. So it will be once again 50 minus 30 or 20 kilonewton. So when you take immediately left of D, that is the next section, 50 minus 30, this complete UVL will be coming for this section, that is minus 20. So 50 minus 30 minus this is resultant load is minus 20 is equal to 0. You will get 0 here. So shear force will change from 20 to 0 in this section. For this section it is constant 50 kilonewton. For this section it is again constant 20 kilonewton. But for the UVL it will change from 20 to 0 in the section CD. Now let us calculate the bending moment at various points. Since the couple is acting at the fixed end, you have to take left side and right side. So extreme end, that is left of A, bending moment is 0 without considering the couple. So there is no force here. So immediately left of point A, the bending moment is 0. So left of A is 0. When you move to the right of A, you should consider this couple, and the couple is acting in the anti-clockwise direction. So minus 33.34 kilonewton meter, and this force will not produce any moment because immediately right of A, the distance part is 0. So the moment of this force is negligibly small. So you will get bending moment right of A is minus 33.34. Again, when you move to the next section, that is left of B, the couple is acting, you have to take left side and right side. So left of B, you have this couple and bending moment produced by this reaction. So this couple will not be considered when you take left of B. So you get minus 33.34 plus 50 into 2. The moment produced by 50 plus 50 into 2. So minus 33.34 plus 50 into 2. So you get the bending moment left of B as 66.66 kilonewton meter. Now when you take the immediately right of B, so moment of these forces, this couple and this force will remain same. Only change coming is this couple will get added. But here it is in anti-clockwise direction, so you should take minus 100. So immediately right of B, whatever value you had for the previous section, that is 66.66 minus 100, that will give the bending moment immediately right of B. So bending moment right of B is bending moment left of B. Whatever value you add for left of B, minus 100, minus because this couple is anti-clockwise, so minus 100, that will give the bending moment right of B. You can again sum up this. Immediately right of B is minus 33.34 plus 50 into 2 minus 100. Okay, so it is minus 33.34 kilonewton meter. Next you have to calculate bending moment at C. So bending moment at C is moment produced by all these forces. A resisting moment minus 33.34, and this will produce 50 into 3 meter clockwise moment minus 30 into 1 minus 100. That will be the bending moment at C. So it is minus 33.34 plus 50 into the distance is 3 minus 100 minus 30 into 1. So that will give minus 13.34. So the bending moment at C is minus 13.34. Bending moment at D has to be 0. At the ends, bending moment has to be 0. Wherever couple acts, then again extreme end, left of A if you take, it is 0. Right of A, this way a couple will come. So here no couple is acting. Suppose a couple is acting, then immediately right of B it will be 0. But left of D, the couple value will be there. Now let us plot the shear force and bending moment diagram for this beam. Now shear force for the first section is constant and it is 50 kilonewton. So you can draw a horizontal line for 50 kilonewton. Okay. Then for the next section it is again constant, means 20 kilonewton. So 20 kilonewton, you can draw a horizontal line. So here the shear force will decrease from 50 to 20 because of this downward point load 30 kilonewton, and 30 will be the decrease, 50 to 20. So right of C we have calculated 20 kilonewton and left of D we have calculated 0. So 20 to 0 is the variation for the section CD. 20 to 0. But due to UVL, shear force will decrease parabolically. So this is parabolic variation. It's not a straight line, parabolic variation. Now this parabolic variation can take place with the concave side up or concave side down. This way also you can show the parabolic variation. But for shear force, both the ways it can vary. But here the major intensity side is left side. So here the concave side will be up. Major intensity is left side, then concave side will be up. If it is in the other way, you will get a variation in the other way with the concave side down. So shear force diagram, parabolic variation can happen in both the ways. So here concave side should be facing top. So wherever major intensity is there you should have a greater slope for the curve. So here you have a maximum slope for the curve and then slope decreases towards the end. So rate of change will decrease. So slope will decrease. Here the rate of change is more because this shear force will decrease more faster than at the ends. So the concave side will face top. If it's in the other way, initially the rate of decrease will be less. So you will get the diagram going like this, and at the end slope will be more. So that is the case when the UVL is in the other direction. So here the concave side is facing up. Now let us draw the bending moment diagram. Bending moment diagram, at left of A the bending moment is 0, right of A the bending moment is minus 33.34. So the bending moment at A will change from 0 to minus 33.34. That change is at A. So it's because of the resisting moment here. So it will change from 0 to minus 33.34. And left of B you have 66.66 kilonewton. So bending moment will change from minus 33.34 to 66.66. And here the variation you have to show by straight line. So always you should join from right of a section to left of next point. So you can join from right of A to left of B. Then left of B to right of B, the change is 100, that is minus 100. So it will decrease at that point. And right of B you have minus 33.34. The bending moment is minus 33.34. That is the right of B, minus 33.34. And at C you have minus 13.34. So right of B to C, the bending moment variation is minus 33.34 to minus 13.34. So the change is linear, so you can plot by a straight line. So this part there will be a straight line, and again from minus 13.34 at D you have bending moment 0. So the variation is going to be cubic variation, a curve with a concave side down. So always bending moment curve, whether it is a parabolic variation or cubic variation, the concave side will be down. But shear force, you can have concave side up or down depending on the position of this UVL. But in this case, always the concave side will be down. So you can plot the cubic variation from minus 13.34 to 0 with the concave side down. So that completes the bending moment diagram. Now we have a point of contraflexure which is coming in this section AB. So you have to take a section and equate bending moment to 0 to get this point, because bending moment is coming to 0 in this point. So you can write down the bending moment equation for this section. This point is coming in the section AB, so you have to take a section here in the portion AB and write down the bending moment equation, and that bending moment equation you can equate to 0 to get this point of contraflexure. So I already marked it as 0.67 meter. So only after solving you will get that distance. So let us write down the bending moment equation for that section. So we are taking a section at a distance x from left end. Now there are only two moments, and that is a resisting moment minus m, and due to this reaction Ra into x. So we know both the values. This is minus 33.34 and this is 50 into the distance is x. So minus 33.34 plus 50x, and you can equal to 0. So bending moment equation for this section is 50x. The reaction is 50 into x, clockwise moment, okay, and minus 33.34. So that can be equated to 0. We get x as 0.67 meter. So this point of contraflexure is 0.67 meter from left end. So this is a point of contraflexure where bending moment changes its sign. Bending moment is also changing its sign at another location, that is at point B. Bending moment changes from positive to negative sign. So this is another point of contraflexure which is at known location 2 meter away from the left end. So this beam has 2 points of contraflexure. One is 0.67 meter from left end and another one is 2 meter from left end. We have drawn the shear force diagram, bending moment diagram, and obtained the point of contraflexure. That completes the problem. That's all for today. Thank you for watching.